In 2022, astronomers using the Murchison Wide Field Array discovered a strange new radio signal that was arriving every 22 minutes. The astronomers were no strangers to such repeating signals. They typically come from pulsars, neutron stars which send intense pulses of light across the universe as they rotate on their axis. But as they began to look deeper into records of past observations, they realized this signal had been arriving at Earth since at least 1988, with remarkable stability, far more stable than is expected for a pulsar rotating every 22 minutes. If it was a neutron star, it was unlike any they had seen before. So, where was this signal coming from? I'm Alex McColgan, and you're listening to the Astrum podcast. Join me today as we grapple with the mystery that lies behind this signal, which will challenge our understanding of some of the most awe-inspiring objects in our cosmos. The location of the source, named GPM J1839-10, is roughly 18,000 light-years away. Its signal arrives as pulses that can last any amount of time between 30 seconds and 5 minutes. These pulses can appear at any time in a window of just over 6.5 minutes, which is centered on 22 minutes after the previous pulse. To us, this may seem like a great deal of variation. 30 seconds and 5 minutes are very different durations, and the pulse arrival varying by over 6 minutes doesn't paint a picture of a very stable source. But neutron star dynamics can be very complicated, and if the source is indeed a neutron star, then many factors can affect the duration and arrival times of the pulses that we receive. Nevertheless, the astronomers were able to spot this signal hiding in data from the last 35 years and used this expanded dataset to average out the fluctuations. They calculated that the source was rotating once every 21 minutes and 58 seconds, as well as how much it had slowed down. But to their surprise, they calculated that this rotation period remained unchanged over the past 35 years, even though it is expected that the source will slow down as it radiates energy into space. We can only say for sure that if the source has slowed down, its rotation period would not have increased by more than 0.28 milliseconds over the 35-year period, because otherwise we would have been able to detect this in our data. This is an absolutely minuscule amount, and it shows that whatever the object is spinning with remarkable stability. This usually isn't odd for a pulsar. These are the timekeepers of the universe, the clocks of the cosmos, mechanistically ticking away with such certainty that we can use them to measure time across vast stretches of the universe. However, this level of stability is odd for a pulsar that is rotating so slowly. To understand what makes it odd, we need to recap how pulsars work and what makes them slow down over time. Pulsars are neutron stars, the leftover cores of dead supergiant stars which, barring black holes, are the densest objects in the universe. Planets like our own are made up of atoms, which consist of over 99.999% empty space due to the vast separation between the electrons and the incredibly dense nucleus they are whizzing around. But imagine an entire star made purely out of the neutrons that are found in the nucleus. No electrons, no protons, no empty space. Merely a teaspoon of it would have as much mass as 11 times that of the entire human population, all 8 billion people. A typical neutron star is around 35% more massive than our Sun, and squeezed into a sphere that has the diameter about as long as the island of Manhattan. To call it dense would be an understatement. For reasons still unknown to astrophysicists, the extreme environment gives rise to an incredibly strong magnetic field. What does this have to do with the signals we receive from pulsars? Where do the light waves come from? To answer this question, we need to understand a complicated process that gives rise to the signal, an exponentially growing shower of light and matter, all spawning from a single electron. Near the magnetic poles of a neutron star, an electron can be accelerated by the magnetic field and emit a so-called curvature photon, tangential to the magnetic field line. This marks, if you like, the start of a pulse. The curvature photon moves in a straight line until the angle between its momentum and the magnetic field line becomes too great. Once this angle reaches a threshold, the light dissipates and imbues its energy into the quantum field of electrons. An electron is created alongside its antiparticle, the positron. The electron-positron pair has some momentum perpendicular to the magnetic field lines, which they spontaneously dispose of in the form of synchrotron photons. These two synchrotron photons can each then produce another electron-positron pair after they reach the threshold angle between their momentum and the magnetic field lines. This process repeats again and again, exponentially increasing the amount of photons and electron-positron pairs created until the synchrotron photons no longer have enough energy to create electron-positron pairs, putting an end to the cascade. These photons then beam out into space, while the original electron continues its journey, generating more curvature photons and more cascades as it moves along the magnetic field lines. This pair production cascade is why the light of a pulsar is so intense that we can detect a signal from this tiny stellar remnant thousands of light years away. But why do we see this light as pulses, rather than a continuously glowing beacon of light shining at us? This is because the magnetic poles of a neutron star are rarely ever aligned with its axis of rotation. Just like on Earth, the magnetic North Pole that our compasses point to isn't the actual geographic North Pole that Earth rotates around. So, the pulsars are like great lighthouses, sweeping their beams of light around the cosmos as they spin. And for an observer far away, like us on planet Earth, we see the beams sweep past us again and again as the pulsar completes its rotation on its axis. These are the pulses of light that our telescopes can detect. However, this is light with very long wavelengths in the radio part of the spectrum, meaning only a radio telescope can detect it. The light that the cascade produced is of the same wavelength, with the peaks and troughs of the light waves fluctuating in unison. The light waves are also polarized, which means they are all aligned along the same axis. This is a hallmark of neutron stars, and this is precisely what we observe in the 22-minute signal. The signal also has fluctuations that last between 0.2 to 4 seconds, where the axis of the light's polarization suddenly changes by 90 degrees, perpendicular to the original axis and then back again. This effect is yet another signature of the cascades at the poles of the pulsars. So much of our data points to a pulsar being the signal that you'd think this was an open and shut case. But one variable that we've mentioned earlier throws this entire theory into doubt: the slow rotation rate of the neutron star. Or rather, the combination of the slow rotation rate and the high stability of the rotation rate of the source. You see, as pulsars lose energy by shining their powerful beams into the cosmos, conservation of energy will ensure that the pulsar slows down. Eventually, the pulsar will slow down so much that it can no longer power the pair production cascades, and the light emission starts to shut off. The pulsar has entered the so-called death valley, the end point on the graph beyond which pulsars should be well and truly undetectable. And yet, we are detecting it. There are other oddities. Other known neutron stars, they usually spin between 10 times a second to once every second. In comparison, our signal has a spin rate of once every 1,318 seconds, over 1,000 times slower than the typical pulsar. This would be fine if it was also slowing down quickly, as such rapid energy loss would power the pair production cascade necessary to light the beacon of the neutron star. Yet, the neutron star is mind-bogglingly stable, and it makes no sense that we can detect it. The astronomers who found the signal considered an alternative mechanism that might explain how a neutron star with such properties might have produced this light. Maybe the neutron star is a magnetar, a neutron star that has an unusually strong magnetic field, greater than 10,000 times the strength of the weakest neutron star magnetic fields. Magnetars are known to undergo starquakes, cataclysmic events that release the tension in the upper crust of a neutron star. These stresses are produced by the strong magnetic fields of the magnetar, as well as the slowing down of the magnetar rotation. A fast-spinning magnetar will bulge in the middle due to the centrifugal force distorting the star from a perfect sphere. As the magnetar slows down, the outer layers need to readjust to a new equilibrium and lose some of the bulge they have. The crust snaps into a new position, causing magnetic fields to temporarily realign and powering the release of the energy as light that we can detect on Earth. The most powerful starquake detected, that of SGR 1806-20 in 2004, released so much energy that if it had taken place as far away as 10 light years from Earth, it would have caused a mass extinction event. If something is able to light the beacon of a dead pulsar, it would be this. So, could GPM J1839-10 be a magnetar that has undergone a starquake? Have we resolved the mystery of the 22-minute signal? It seems not. We expect these starquakes to also emit light in the X-ray part of the spectrum, yet no X-rays can be detected from the position of the source roughly 18,000 light years away. It also wouldn't make sense for a magnetar outburst to be going on for 3 decades. The starquake is a temporary phenomenon, and the energy dissipates within a few years at most. It is simply incomprehensible that this signal would have existed for 35 years if it was indeed a magnetar. Once again, the unique properties of our signal exclude it from being a neutron star, even an unusually powerful one that has undergone a special event such as a starquake. But what else could the source of this mysterious signal possibly be? The astronomers who discovered the signal proposed a few alternatives for the identity of the source. One possibility is a highly magnetic white dwarf. A white dwarf is another type of remnant left from the recent death of a star, but one that didn't have enough mass to collapse the empty space in the atoms to become a neutron star. A remnant that has an unusually strong magnetic field could produce radio emissions, and as it is not a neutron star, it could get away with being as slow and stably rotating as the source of our object while doing so. The issue is, this would require an exceptionally strong magnetic field, greater than any we have spotted on a white dwarf. AR-SCO is the only known radio pulsar that is actually a white dwarf, and its radio emissions are 1,000 times less luminous than the source of our 22-minute signal. So, if a white dwarf is unlikely, what are our other options? Astronomers have observed low-frequency radio waves coming from the interactions between stars and exoplanets, as well as a binary of 2 brown dwarfs rotating around each other, but this emission is typically weaker, around 100 million times weaker than the source of our signal. In the end, it seems like none of our theories can explain the 22-minute signal. While the unresolved question about the source of the signal may feel frustrating, this is precisely the kind of mystery that astrophysicists look for. When scientists find new data that challenges our long-held theories, they can usher in revolutions in our understanding of the universe around us. Here, our already shaky understanding of neutron stars is being challenged. The astronomers are confident that the ease with which they identified this signal means similar sources lie out there in the galactic plane, waiting to be identified. Just like GPM J1839-10, the other signals might already be lurking in the data we have collected. Identifying more of these signals will shed light on the process powering a mission beyond the neutron star Death Valley. Whatever lies behind the 22-minute signal, we are sure to learn of an entirely new phenomenon that we have never seen before. That's all we have time for today. I hope you've enjoyed listening to this podcast on the mystery of the 22-minute radio signal. If you like what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.